7.5 quantitative changes in equilibrium system. If you have the system of reaction A reacted with B, give you the products C and D. This is the K constant. How do we write it? And you need a different temperature, you have a different K constant. We have the K constant happen at equilibrium. The equilibrium have reached. This is the concentration that you see here is for concentration of the product, concentration of the reactant at equilibrium. When the equilibrium is not reached, we call it Q. Q constant, it would be the same thing, but this concentration that you have, concentration of the C, which is your product, and concentration of the D, and is your product to the power of its coefficient divided by A to the power of A, P to the power of D. When the Q and K are the same, when the Q and K are the same, we say the equilibrium reached. But when the Q is greater than K, what that means? If the Q is greater than K, means your numerator is much more bigger than it should be. Means your product is much more than the equilibrium state. That's why you need to, if you wanna, it wanted to reach equilibrium, the reverse reaction need to happen. Make sure you wanna decrease the concentration in C and D. So it go to the reverse direction. If the K is bigger than Q, or Q is less than K, means you need to increase the concentration of C and D, or Q is the same as K, right? So to increase that, the reaction need to go forward. So let's just look at the question. In a container 450 degrees Celsius, nitrogen and hydrogen react to produce an ammonia. The equilibrium constant K is given to you. When the system is analyzed, the concentration are found to be 4, 2, and 2.2. So concentration of each of this is given to you. Determine whether you are at equilibrium. If not, predict the direction of this reaction. Again, K constant, we establish K constant. Concentration of the product to the power of 2, HN3 to the power of 2, divided by concentration of N2 to the power of 1, because the coefficient is 1. Concentration of H2 divided by to the power of 3. The concentration of each of that is given. You just put it there, you get the Q. You also know K. K is given to you to be what? 0.064. Okay. So 0.64 is K is greater than Q, right? If the K is greater than Q, means this number here, you need to increase this number to make the Q to be higher than that, right? So you need to increase this. To increase this, you need to go forward. That's why the forward reaction which will happen to help it to reach equilibrium. The following reaction occur in a closed container at 445 degrees Celsius. The K constant is given. Is the system at equilibrium? So for A, the concentration of each is given. Again, we establish Q. We put this concentration Q now is that. So comparing to the K, which is 0.02, is exactly this Q is the same as K. So it's equilibrium, right? So we do the same thing with the B, concentration of B is given. So you put that there for the Q is 0.34. As you see, this is greater than K. If this is greater than K, so it means you have to decrease this, decrease your product. So decreasing the product, you have to go backward, right? The backward reaction happening. So to do practice, question 1 and 2. Here's another question. Hydrogen iodide is a compound used in the production of the hydriodic acid. HI is produced by reacting hydrogen gas and iodide vapor according to the following equation. The equilibrium constant K for a reaction is 49.7 at 458 degrees Celsius. Calculate HI concentration at equilibrium if the concentration of the other two entities is 1.07. 1.07 for H2, 1.7 is 1.07 for I2. You want to find concentration of HI. Again, we establish K constant equation. Since the concentration of H2 and I2 is given and K is given, the only unknown is HI. We'll just rearrange for HI simply to calculate concentration. Here's another one. A sulfur trioxide is compound used in production of sulfuric acid, is produced by reacting sulfur dioxide, SO2, with oxygen gas according to the following equation. 2SO2 react with oxygen, give you 2SO3. Calculate the equilibrium concentration of oxygen if 1.5 mole per liter of SO2 and 3.5 mole per liter of SO3 are found in an equilibrium mixture of this system at 600 degrees. So again, you can establish K constant from this reaction. Then K constant is given to you, concentration of SO2 gas and SO3 is given. You just need to rearrange for oxygen. To do this, to practice, do question number 3 and 4 here. Calculating equilibrium concentration from initial concentration. So here is the one that we use the ice table again. So carbon monoxide react with water vapor here to produce carbon dioxide and hydrogen. At 900 degree K is given to calculate the concentration of all entities at equilibrium if 4 mole of each entities are initially placed in 1 liter of the closed. So it means I have 4 mole of that, 4 mole of this. To convert it to concentration, 4 divided by 1 will give you mole per liter. So since the K constant is given to you, instead of each entity are initially placed, means all of these entities for CO, H2O, CO2, and H2. All of that is given. If you just establish Q, we'll see that the Q is 1 mole per liter, right? Okay, look, the K was 4.2, and here is 1, right? So Q is less than K. And you need to increase Q in order to be equal to the equilibrium state. So increasing Q means you increasing your numerator. You increasing the product means the reaction need to go forward. So you have a forward reaction. This is very important to determine which direction you need to go. Then you can establish your ice table. Here is your ice table. So again, you write your reaction at the top. Initially, you have 4 mole per liter of each entities. Since this is forward, the concentration of CO and H2O decrease. By how much? By X. That's why it's negative X. And concentration of these two increase, that is positive X. For equilibrium, it's just 4 minus X, 4 minus X here, 4 plus X, 4 plus X. Then we just establish our K instead of this CO2, which is that there, put 4 plus X. Instead of H2 concentration, we put 4 plus X, CO 4 minus X, H2O 4 minus X. You can find in the last row here what to put for each concentration. But this is we have. So here, both the same, so it's power 2. These two multiply by each other same, that's why it's power 2. So we square root both sides together of these power 2's. Then cross multiplication, 4 minus X multiplied by this number here. you expand, you bring the x to one side, bring the number to one side, you rearrange it for x. X is 1.37. To find the concentration of each at equilibrium, just we find x, you put the value of that everywhere. To find the concentration of each entities at equilibrium, as you see, they did it here. Okay, if you want to check if your number is right or not, just simply put it in Q. See the Q is the same as your K, so it means that's true. This is the concentration at equilibrium. Here is another question, similar. Iodine and boromide reacted in a closed 2-liter container at 150 degrees to produce iodine monobromide. According to the following equation, the K constant is given. What are the equilibrium concentration of all entities mixture? If the container initially contained 4 mole each of iodine and bromide. So iodine initially, bromine you have, it means you don't have any IBR. You just find the concentration of that. So 4 divided by 2 is 2. So concentration of I2 and BR2 is 2. And IBR, we have nothing. Of course, if you have nothing here, is go forward, right? That's why when you are putting the ice table, you know, it's forward equation. Initially, you put 2, 2 here and 0 here, nothing. So since this is forward, it's going to be 2 minus x, 2 minus x, 0 plus 2x, because this is coefficient is 2. So you have your equilibrium. So you establish your K. IBR, we put 2x power 2. I is 2 minus x, BR2 is 2 minus x, multiply by each other. You have 2 minus x power 2. Again, you can square root both sides, cross multiplication, bring x one side, and rearrange for x. When you find the value of the x, you can put it simply here to find the concentration of the each entities at equilibrium state. Then you can check your answer. Here is another example. When hydrogen react with fluorine, hydrogen fluorine is formed according to this. The equilibrium constant is given to you. The concentration of all entities at equilibrium is 4 mole, and F2 is 4 mole, HF is 6 mole, and you place it in 2-liter of container. So of course you can find the concentration 4 divided by 2, 4 divided by 2, 6 divided by 2. So you find the concentration of each entity. You will find Q. Q, you establish the equation for the Q, you put it there. You just compare the Q and K, right? So for Q, as you say, Q is less than big. Okay, so this is 1, 1, 5. Of course, K is greater, right? So since the Q is less than K, you have to increase the value of Q. So need to increase your product means you have to go forward. The reaction is forward again. And when you establish the ice table, so forward means you have to put this negative x, here's negative x plus 2. And on top, you put your initial concentrations. And at equilibrium, you have 2 minus x, 2 minus x, 3 plus 2x. Then you establish your K constant for each of these entities. For HF, for example, here, we have 3 plus 2x. So here is power 2 is there. H2 concentration is 2 minus x. F2 concentration is 2 minus x. You put it there. Now, again, here is 2 minus x power 2, right? We can square root both sides to get rid of this square part. Cross multiplication, rearrange for x, and again, you have value of the x. You can put that to the equilibrium x here to get concentration of the each entities at equilibrium state. And at the end, you can check your answer. Okay, to practice, please do question number 5 and 6. Here is another one. How about if the K is very small in this case? Again, you have K constant for your reaction is given. we have initial concentration 0.25 mole of CO2 that is given us, and we don't have any CO and O2. So we turn this one into the mole. The liter, you place that in 1 liter container. So it's just simply 0.25 divided by 1 is 0.25. This concentration of CO. We do not have any concentration of heat for this. Of course, it's going to be 4, right? Because no concentration of that is given. So here is the change for CO2 is minus 2x, see the coefficient is 2. Here is plus 2x, the coefficient is 2 here. This coefficient is 1, so it's going to be plus x. And at equilibrium, 0.25 minus 2x, 0 plus 2x, here is 0 plus x. To establish your k is given again. Instead of CO, you put 2x. Instead of O2, you put x. CO2, you put 0.25 minus 2x. Okay, looking at this, since we can use the 100 rules. Okay, be careful how we do that. 100 rules saying that if you divide this constant 0.25 divided by this k here, which is 6.4 10 power negative 7. If that is bigger than 100, which is, if you put that in a calculator, you see it's bigger, much more bigger than 100, then you can eliminate this variable here. And it's just 4x power 3 divided by 0.25 power 2 equal to this number. This is 100 rules. See, we eliminate that 2x, and this is what we have. Then we cross multiply, we rearrange it for x, and the x, you find it this way. Then when we find x, you can put it back x here to find the concentration of each entities at equilibrium. At the end, you can check your answer as well. So let me erase this. Here is another example. I believe this example, guys, you can do it. Again, when we establish this, we can use the 100 rule. 0.4 divided by 1.6 10 power negative 5 is greater than 100. So I can eliminate this 2x here. While I'm doing this, this is what we have. We rearrange it for x, and that would be the same. For practice, you can do question number 7 and 8. Sometimes, if you want to do this, we will get a quadratic equation. Use the quadratic formula. I hope that you remember from the Wheelen's function. So quadratic formula is when you have quadratic equation like ax power 2 plus bx plus c. A is the coefficient of the x power 2, b is the coefficient of the x, and c is the constant. So then answer to this equation is negative b plus minus b power 2 minus 4ac divided by 2a. Here's the example. After you establish the ice table, establish your k, we get to this point. We do a cross multiplication. 2.5 minus x multiplied 4.5. Let's see here, 4x to there. 2 power 2 is 4, x power 2 is there. You bring everything to one side. So you bring everything to expand, you bring everything to one side, and see here, we have a quadratic equation. The a is 4, b is 4.5, c is 2.25. You put it there, you calculate, we have two x's. The x positive is acceptable. You do not have a negative concentration. Then again, the same way, you just put the x in your equilibrium concentration, and you find the concentration of each entity is at equilibrium. At the end, you can check your answer. Here's another one that you have to treat it the same way. You can You can use the quadratic formula for this. I would like to see you student checking this question yourself. Question 9 and 10, you do as practice.